Welcome to the Single-Engine High-Wing Electrical System Video Series, Volume 4. The content of this presentation is for reference only and does not contain instructions for continued airworthiness. The approved procedures in their entirety are set out in approved technical publications. In Module 4, we are going to look at the aircraft electrical system maintenance checks that are called out in the Aircraft Maintenance Manual. The electrical system components on these aircraft are largely replaced on condition. The only component we can currently recommend changing on a time-based schedule is the avionics switch every 500 hours of aircraft operation. Otherwise, all of our component replacement is done to address specific squawks from flight crews or when we find a fault while performing our scheduled maintenance inspections. When we look at the inspection time limits in 5-10-01, we find a number of electrical system inspections. The general condition and security checks are fairly self-explanatory, so we'll skip most of those as we run through this list today. Our first inspection has us looking at the alternator installation. Let's take a moment to look at the belt tension check. It's easiest to do this check with a torque wrench that has a dial indicator or a digital display. We are looking for the amount of torque it takes to make the alternator pulley slip against the belt. So a tool that will record the peak torque applied before we reach the breakaway point or maximum static friction will be helpful. We can use a standard hex socket over the pulley nut or use an internal wrenching socket inside the alternator shaft. As we rotate the pulley and observe the belt slippage, we need to record the applied torque at which the slippage occurs. If the recorded torque is above or below specification, the belt tension will need to be adjusted accordingly. The next check that we will be looking at is the standby battery capacity test. There are two methods for performing this test in the aircraft or on the bench. The on-aircraft test simply involves operating the avionics as stated in the manual and observing the battery voltage. If the battery voltage remains above 20.0 volts for the duration of the test, the battery passes. If the battery voltage drops below 20.0 volts before the time is completed, discontinue the test. Remove the battery and bench charge it, then try the test again. If the battery again fails to maintain minimum voltage throughout the required time, do not return the battery to service. After a battery passes the on-aircraft cap check, it will require removal for recharging before it is returned to service. We recommend moving the battery to a well-ventilated area for charging. If you have a capacity tester for 24-volt lead-acid batteries, you can use the bench procedure for testing. Both methods require charging outside of the aircraft. Any typical 24-volt AGM charger is fine. The battery manufacturer does not define any special equipment required for these batteries. For both methods, you may need to fabricate an adapter to connect the standby battery's round 4-pin connector. The part numbers can be found in the wiring diagram manuals and can be ordered through Textron Aviation Parts Distribution. It is worth noting that in the past, the standby batteries were not required equipment for U.S. VFR operators, so many have chosen to defer maintenance on these batteries. With the dual electronic ignition systems installed in the newer aircraft, the standby battery becomes a required safety item for all operations. Proper maintenance of these batteries becomes critical for dual EIS aircraft. If equipped with a GI 275, we also need to test the instrument's built-in battery. The GI 275 has its own built-in backup battery test. The instrument is booted in config mode, and the backup battery test is performed by selecting this test from the on-screen menu. The standby instrument will automatically record the results of this test. The ACU overvoltage protection test is another check where we are given a couple different ways to comply. If you don't see these aircraft very often and can't justify the expense of a Lamar TE-04 MCU test set, you can easily fabricate a harness for performing this test. The Aircraft Maintenance Manual gives us instructions for connecting a pair of 9-volt batteries into the electrical system with a couple of alligator clips to make temporary connections. We remove the orange overvolt sense wire from the top of the battery contactor and add these two batteries in series with the ship's battery. This is what the setup looks like in real life. This puts about 42 volts into the sense line and should cause the ACU to ground its power input wire, popping the 5-amp alternator circuit breaker. If this happens, the system is functioning normally. Let's look again at this test using the wiring diagram. The first thing to note is that the diagrams often show the sense wire tied to the alternator relay. This is not how Lamar actually builds the MCUs. The orange sense wire picks off of the same bus, but physically it's connected to the battery relay instead. When we install our overvolt test harness, we add 18 volts to the ship's battery to cross that overvolt threshold. If we have 24 volts at the ship's battery and we add two 9 volts, that will give us about 42 volts of input. Fresh alkaline batteries will be a little bit above that, but that's okay. The reaction time of the ACU is based on the severity of the overvoltage event. A weak ship's battery or weak 9 volts may cause the trip reaction to be slow, or you may observe no trip at all. Proceeding with this test, we'll observe the alternator field circuit breaker. When we close the master alt and bat switches, this will send power to the alternator contactor, the ACU, and the battery contactor. This will allow voltage from the ship's battery to run in series through the 9-volt batteries, presenting an overvolt condition to the ACU's sense circuit. This will prompt the tripped circuit breaker, removing power from the ACU and the alternator relay. If we are using the Lamar TE-04 test set, we will need to patch the box into the aircraft electrical system. The test set has an alligator clip for the alternator feed and an ACU connection, the J1 main control harness, and the J2 power disconnect. Most of these are straightforward, but the J2 power disconnect is a little different. Since the MCUs can be configured for anything from a 2 output to a 5 output system, your MCU may have only a 2-pin, only a 3-pin, or a 2 and a 3-pin connector here. If you have an earlier version with only 2 buses, you'll use the 2-pin connector and leave the 3-pin dangling. For all others, you will use the 3-pin only and leave the 2-pin dangling, as pictured here. With all of our connections made, we'll start the test following the LI-0021 manual that is included with the test set. We will start with a lamp test to verify all the indicators on the TE-04 are working properly. Next, we will verify that normal operation looks correct with power available from all of the fuses and or breakers as applicable. We could ignore the red low voltage light, but we should see no other fault lamps. As we proceed through the checklist, we come to the overvoltage test, where we will move the OV switch to the test position and hold for 5 seconds. We should observe the ACU trip light illuminate and the ACU power, field, and alt relay lamps should extinguish. Note that the alternator field circuit breaker should not open. While testing, the TE-04 is between the MCU and the aircraft wiring, so it has removed the power from the ACU and the alternator contactor before the aircraft circuit breaker opens. If the OV test fails, the test set manual has instructions for troubleshooting that we'll discuss in the next video. The final item from the aircraft maintenance manual that we will look at is the essential and cross-feed bus diodes. In a previous video, we talked a bit about these diodes and a simple pre-flight check on the diodes that feed the essential bus. This test will be a little more involved and test the diodes between the main buses and the cross-feed bus as well. The landing and taxi lights are on separate buses, so that gives us a convenient checkpoint on some airplanes. This procedure was written before the incorporation of the current LED landing and taxi lights. Unfortunately, the unified LED landing taxi light assemblies limit the abilities of this test, as there's no way to get a landing light on without a taxi light. For these airplanes, it may be helpful to remember that the red flashing beacon is on bus 1 and the navigation lights are on bus 2. First, we'll want to make sure all the lights are functioning normally. Next, we will remove power and open up the J-box. In this example, we will talk about the more modern configuration with circuit breakers, but if you have the older version, you can just pull the fuses with the same result. The aircraft maintenance manual first has us remove the connections from the F1 and F3 breakers to remove power from bus 2. Yes, by design, F1 feeds bus 2 and F2 feeds bus 1. In some MCUs, F1 and F3 were inadvertently swapped, so it's good practice to just pull both while you're in there. Power on the airplane using the master bat only switch and turn on the landing and taxi lights, or beacon and nav lights depending on how your aircraft is equipped. Only the landing lights or beacon should illuminate as the taxi and nav lights are powered on with a disconnected bus 2. If both lights are on, that's indicative of a bad diode or other wiring fault. The AMM also has us look at oil pressure to verify power is getting to the GEA, as it is normally powered by bus 1 as well. If that all checks good, we will power down, reconnect F1 and F3, disconnect F2, and do it all over again. This time we expect to see only the taxi light or nav lights on, and the GEA should still be giving us a low oil pressure warning, as it should be getting power from the essential bus. If that all checks good, we'll shut everything down, put everything back the way it was, and make sure all the lights are operating normally before returning to service. If you still have that Lamar TE-04 test set installed from doing the overvoltage check, you can use this to your advantage for the diode check. Instead of pulling leads from breaker terminals, you can simply pull the inline fuses to take the individual buses offline. Verify the appropriate bus lamp extinguishes on the TE-04 and do the same checks with the lights and the GEA. Don't put away that TE-04 quite yet. We'll talk about that more in the next video as well. If we do find a system fault and need to access the diodes, you can roll the breaker panel aft out of the instrument panel and isolate some circuits. There is a diode check in the manual that uses a fluke meter, but sometimes we see diodes that will pass a check with a very low current level, like with a meter, but it will fail when we put a larger load on the circuit, like landing or taxi lights. So keep that in mind. This wraps up our look at maintenance procedures for the Cessna single-engine high-wing aircraft. The next video in this series will discuss troubleshooting the aircraft electrical system. Thanks for hanging out with us today.